Hello, everybody. Dr. White here. Going to talk about a few more continuous type distributions. The exponential distribution, gamma distribution, chi-square distribution. So all these start from the thought about a Poisson process with some rate lambda events per unit time on average. Okay. And we'll introduce the idea of the reciprocal of the rate, theta. So like if you're doing lambda events per hour on average, then you'd expect to wait 1 over lambda theta time between events, like 2 events per hour, expect to wait 1/2 an hour between events. We're going to use this notation occasionally. All righty. Let's let W be the time to wait for the first event. And let's see if we can get the probability distribution for W. All right. Well, let's go for the CDF, capital F of little w. So that's the chance that capital W is less than or equal to little w. Now, for sure, if little w is less than or equal to 0, this chance is nothing. You know, the chance of getting your first event in 0 seconds is 0. The chance of your first event in -2 seconds is 0. But how about for some positive waiting time, little w? What's the chance? Well, the chance that it takes less than or equal to little w units of time is 1 minus the chance that it's going to take more than little w units of time. But let's think about that event. That event is the same as the event that there are going to be 0 events in the time interval from 0 to w in that Poisson process. And this is going to be an easier probability to think about. Let me define this random variable x sub little w. It's going to be the number of events in that time interval from 0 to w. Well, this is a Poisson process, so x sub w has got to be a Poisson random variable. It's a count of events in a time interval. It's a Poisson random variable. What's its rate, though? Well, the rate for the process is lambda events on average per unit time. So the rate for xw is going to be lambda times w. You know, like if w were 2, then you'd expect 2 lambda events during that time. Okay, so we've got the distribution of x sub w. Therefore, we can figure the chance that x sub w is 0. And that's just the PMF for a Poisson at 0. So rate to the 0, e to the minus rate over 0 factorial, which works out to e to the minus lambda. Great. So that is the probability up here that we were looking for. And so we plug that in, and we get that capital F at w is 1 minus e to the minus lambda w for w bigger than 0. So writing down everything we know now, that's the piecewise defined function that makes capital F the cumulative distribution function for capital W. So if we take its derivative, then we can get ourselves a PDF. So we do that, and the derivative of 1 minus e to the minus lambda w turns out to be lambda e to the minus lambda w, for the w is bigger than 0. Of course, it's 0 otherwise, because the derivative of 0 is 0. So we'll just say what it is on the support and move on. Now, the way your book writes this is they use the thetas rather than the lambdas. They use the average time between events rather than the average number of events per unit time. So they're going to write a 1 over theta for the lambda. And of course, once you've formally set up a random variable and you want to post it on some list of table of random variables for people to look at and study, you tend to call your random variable capital X and possible values of it little x. So the way you'll see this in the tables is that the PDF is f of little x is 1 over theta e to the minus x over theta. Support is the positive real numbers. Okay. So that's an interesting random variable, the time to wait for your first event in Poisson process. You ought to give it a name. We call such waiting time variables exponential random variables. So we'll say that capital X is exponential with parameter theta. We could also say that it's exponential with a rate lambda, depending on which of the concepts, rate or waiting time we prefer to use. Of course, we say it's an exponential random variable because look at the graph of the PDF. It's the graph of an exponential function. When x is 0, we're up near 1. Well, when x is close to 0, we're up near 1 over theta, and then we go down exponentially. Little side note, in a Poisson process, you'll remember our definition of Poisson process is that the number of events that occur in disjoint time intervals are independent random variables. So suppose that you let xi be the waiting time from the I minus first event to the ith event for each I. So x1 is the waiting time from the 0th to the first event. That's the exponential random variable we were actually working with. x2, the waiting time from the first to the second event. x3, and so on. Each one of these is actually an exponential theta random variable because of this independence. It doesn't matter how long it took to get to the first event. That's not going to affect what happens in subsequent time intervals. And so the time to wait for the second event has got to have the same distribution as the time to wait for the first. Well, the additional time to wait for the second has to have the same distribution as the time to wait for the first. And so the x2 is also exponential. Similarly, the x3 and so on. And they're all independent of each other. Let's go for the moment generating function for an exponential so that we can apply that and maybe get the expected value and the variance. So moment generating function is expected value of e to the t capital X. So we integrate over the support, possible values of e to the t little x times the chance of getting that value. And we have an improper integral, so I'll go ahead and set it up the right way. Limit as some number goes to infinity, the integral from 0 to n. And I see two factors involving an e, so I'll go ahead and combine them with a rule of exponents. And I'll pull out that constant 1 over theta. And then the antiderivative of e to something times x is e to that same something times x over that something. And evaluate between 0 and n. And so we plug in n. We get this. I've multiplied the 1 over theta. Multiply that theta in on the bottom. We also have minus what you would get by plugging in 0. Now e to the 0 is a 1. And on the bottom, we would have, if I multiply in the theta, I'd have a theta t minus 1. I've got to minus it, so I can write that as a plus 1 over 1 minus theta t. So when is this limit going to be finite and when not? Well, you got an exponential function there. If the little coefficient in front of the variable n, if this little coefficient is a negative number, you're looking at, something like the graph of a y equals e to the negative x. It goes down really fast to 0, converges to 0. And so if t minus 1 over theta is less than 0 here, then this integral is going to converge. If it's bigger than 0, then this integral is going to diverge because e to the positive power goes up. So when we get the convergence, this stuff here is going to 0, and you're just left with, this. So the moment generating function is 1 over 1 minus theta t for t's that are less than the rate, 1 over theta. So the moment generating function is perfectly well defined for this random variable. The lambda is a positive number, so I can definitely find a small interval minus h to h surrounding 0 where the moment generating function is defined. And we're okay. So if you want the expected value and the variance, then of course you would take the derivative. And to do that, I would set myself up. Here's the moment generating function. I'll write it as power. I'll just use the power rule and the chain rule, and you get to this. And then I can set that up as, again, a power constant times function to the negative 2. Apply the power rule again, and it comes out to this for my second derivative. So, got a little typo here. I wanted to say m prime of 0. I accidentally wrote something that looks like a theta. M prime of 0 would be, let's see here, put in t as 0, and you get a theta over 1 squared. So you get a theta. So that's the expected value, the mean of an exponential random variable. And it makes total sense. The theta is supposed to be the average time between events, because it's 1 over lambda. So it should be the expected value of the time to wait for your first event. As far as the variance, plug in zeros and do your work. And the variance of an exponential theta is theta squared. So the standard deviation would be theta. So typically, an exponential random variable would come out somewhere between the mean of theta minus the standard deviation, that's a 0, to the mean of theta plus the standard deviation, step 2 theta. Some other useful facts about exponentials. If you were to calculate the median, you see the textbook, or just give it a try now, like stop the screencast and see if you can do it. The median comes out to theta times the natural log of 2. One of the most useful tricks involving exponentials is just to remember what's the chance for them to be bigger than a number. What's the chance that it takes more than little x units of time to get your first event? So that would be 1 minus the chance that it takes less than or equal to x units of time. So it's 1 minus the formula for the CDF. And so that's very simple, e to the minus lambda, and whoops, that is a typo, that w there should be an x. So that's equivalent to e to the minus x over theta. So that should remind you of geometrics. Geometrics are the waiting time until your first success. They must be really similar to exponentials. And if you think about geometrics, the chance that a geometric is bigger than x is, well, that would mean that your first x tries have to be all failures, so 1 minus p to the x. So really quite similar behavior as you would expect. One of the odd-numbered exercises in the section is about the memorylessness property of exponential random variables. So let's say capital X is exponential theta. And so here you are, you're waiting for your first event. And let's say you've waited little x units of time, and the event has still not occurred yet. So capital X, whatever it is going to be, is bigger than little x. And so there you are at x units of time, and you're wondering like, wow, how long am I going to have to wait for this to happen? How much longer am I going to have to wait for this event to happen? And so you're asking like, what's the probability that capital X will be bigger than the x units that have already waited, plus another y units of time? What's that chance that I'll have to wait at least another y units of time? Well, it's a conditional probability, so it's the probability of A and B over the probability of B. And when I look at this event here, for x to be bigger than x plus y and bigger than x, that's just the same thing as x being bigger than x plus y. If I'm bigger than 5 feet and bigger than 7 feet, it's just I'm bigger than 7 feet. And the chance for an exponential to be bigger than a number is something we've already figured out, e to the negative number over theta. And on the bottom, we got an e to the negative x over theta. So there's a property of exponentials on the top, and we see there's a little cancellation, and we're only left with e to the minus y over theta, which is exactly the chance for the exponential to be bigger than y. And so if I've been waiting x units of time, and I'm still waiting, then chances for the next event are just as if I was at the very beginning of the process. It's kind of like it didn't do any good, all of that waiting for x units of time. It didn't bring an event any closer or make it more likely to happen. And so we call this the memoryless property. It's like the Poisson process has no memory of what happened before. Having no events before doesn't make events more likely coming up or anything like that. And by the way, you've already shown, I think, in an earlier exercise, the geometric random variables also have a memoryless property. Okay, so that was a lot of fun, analyzing what are the chances when you're waiting for the first event to occur. But suppose you want more. Say alpha is some whole number, 1, 2, 3, or bigger, and you're waiting for the alpha event to occur. So you start off at time 0, and you wait, and you get an event, and you get an event, and you get an event, and maybe you're waiting for the third event, so you stop. What's the distribution for that time? So once again, let's set up a random variable. Let's let capital W be the time to wait till the alpha event. By the way, we're going to call such waiting random variables gammas. And we need 2 parameters to specify them. We need to say how many events we're waiting for, that's the alpha, and we need to say something about the rate of the process. And so we could specify the average waiting time between events, theta, or we could specify the rate of the process, lambda. So you'll see it written different ways in different treatments, different books. Trying to find the distribution worked pretty well with just exponentials, so it might work well with gammas. Let's give it a shot. Chance you wait less than or equal to little w units of time is 1 minus the chance that you wait more than w. And if you wait more than w for your alpha event, then that means that in the time interval from 0 to w, there must have been fewer than alpha events. So set yourself up a little random variable, I'll call it xw, that's the number of events in the time interval from 0 to w. And let's think about the distribution of that random variable. This switching around from the waiting to the counting is a really useful idea. Well, anyway, that's Poisson random variable. And its rate would just be the width of this interval times the rate of the process, so its rate would be lambda w. So we can figure out the chance that xw is less than alpha. All we got to do is add up the PMF for 0, 1, 2, 3, all the way to alpha minus 1. So I do that here with an index variable k in this summation. And so rate to the k, e to the minus rate over k factorial. And so that would be a little formula for capital FW. And now, very sad, I'd like, oh, no, sorry, not sad, looks like I'm okay. Thought I had a typo. Let's go and see if we can get the PDF, little f of w, okay? And to do that, I'm gonna have to take the derivative of capital F, but before I do, I want to just rewrite capital F a wee bit. I'm gonna siphon off the k equals 0 to be its own little thing standing out here. When k is 0, it's rate to the 0, e to the minus rate over 0 factorial. It'll just be an e to the minus rate. And that's a minus here because of this minus. And then I'm going to have to subtract off the rest, so the sum from 1 to alpha minus 1. Okay, so that's capital F rewritten. Now let's take the derivative. And we come to our PDF little f. And so this part just comes to this. And in this part here, it's a derivative of a sum, so it'll be sum of derivatives. And each one of these, well, it's a product of two functions of w. So I'll need to use the product rule. And when I do, I'm going to end up with like all of this. So I'll let you stop the screencast and maybe do computations yourself and see if you can actually come to this. But I swear it works. It's derivative of first times the second factor plus the first times that derivative of that second factor. It really works. And I can simplify a little bit here. I'm looking at this stuff here, and I see that it has a factor of e to the minus lambda w, and then this stuff here also has that factor. So I'll pull that out of the sum sign. I also see that there is a lambda hanging about here, and there's a lambda hanging around here. And I'll pull that out. So I've pulled a lambda e to the minus lambda w out of the sum sign. And thinking about what's left, I've got a lambda w to the k minus 1. Now I've also got a k, but that's going to cancel with this k factorial a little bit, leaving just a k minus 1 factorial. Over here, I'm just going to have my minus that I never pulled out, and my lambda w to the k, and it can't do any canceling. So after I've broken up into two fractions, it's going to look like that. And then I'll go ahead and just write out this sum. So this is the k equals 0 term, and this is the k is 1 term. And it keeps on going like this all the way up to the k equals alpha minus 1 term. And lo and behold, there's a bunch of cancellation. This little minus here, minus lambda w to the 1 over 1 factorial, cancels this plus term here. And this minus term here cancels the term that you just don't see written coming right after it, the beginning of the k equals 2 term. And that kind of cancellation is going to keep going. And so in the end, that whole sum just telescopes down to the first part of the first term and the last part of the last term. Everything else gets canceled out. Wonderful little telescoping sum. And so we're just left with this. And so you can distribute the lambda e to the minus lambda w through, and you'll see there's a little bit more cancellation, and it all simplifies down to this. So, woohoo, we have the PDF for our gamma random variable. And of course, what you'll see in the book is they'll change the little w to a little x, and they'll call their random variable capital X. But before we do that, let's do a little detour. And I want to show you something cool and show you how it unexpectedly hooks into what we've been doing so far. I want to define something called the gamma function. Capital gamma there. It's a function of any positive real number t. And it is this improper integral from 0 to infinity, of, and oh, I have a typo, y to the t minus 1 e to the minus y, and that should be a dy, not a dt. dy. I've got it correct down here. I just forgot to correct it. And so because there's a t in it right here, then that improper integral will deliver different values for different values of t. It's really this function of t. So let's find its values for a few t. Let's try, what is it when t is 1? And so you're looking at the integral from e to the minus y dy. And so you could just, go and set up the improper integral and get the antiderivative and do all that and take limits. But I'm kind of a lazy guy, okay? And I just noticed that if I write this a little differently, if I say that it's 1 over 1 times e to the minus y over 1, which is totally legal to do, then what I'm doing is taking the PDF for an exponential with theta equal to 1. And I'm integrating it over its support, 0 to infinity. Therefore, that integral has to be 1. So you'll see this a lot, not a lot, but quite often in probability situations. You can avoid having to do an integral because you can recognize the integral as being related to the integral of a PDF over its support. And that would be 1. So anyway, gamma of 1 is 1. Now, let's try gamma for any old t again. So it's like this. But let's do integration by parts on this and just see what we get. So I'm going to make the choice in integration by parts to let u be y to the t minus 1, this little part right here. And so that means that dv has to be everything that's left, e to the minus y dy. And then v would be the antiderivative of the dv, and the antiderivative of e to the minus y dy is minus e to the minus y. And I need to get du. And so that's going to be, well, I go up here, so that's a little function of y, and so it's going to be t minus 1, y to the 1 less power, so that's a t minus 2, and that should be a dy. So I got a typo there. It should be a dy. And then I go and apply my integration by parts. So remember, the integration by parts says, okay, the antiderivative is going to be a uv minus the antiderivative of v du. So here is my u, is this minus e to the minus y. I'm sorry, that's my v. And my u is my y to the t minus 1. So that whole thing is a uv. Now, ultimately, I'm going to integrate from 0 to infinity, so I need to evaluate that from 0 to infinity. Oops. And then minus the antiderivative of v du. Okay, so here's my v, and then I need my du, and my du is this stuff times dy, and so here we see this stuff right here, and again, that should be a dy. Sorry. So let's see. Let's go ahead and grab this. If we plug in like an infinity, which mean for y, so that means imagine the y getting bigger and bigger. Well, e to the minus y is going to get really small really fast. Now, y to the t minus 1, that could get big, go to infinity, but it's a power function. y. Although it grows, and grows maybe fast, it does not grow any near as fast as that shrinks to 0. Like if you try L'Hopital's rule and stuff on it, you'll find that this product here has to go to 0. So you'll get a 0 when you plug in the infinity. And if you plug in the 0, then you've got a 0 to the t minus 1, which is a 0. So that whole thing is going to have to work out. Now over here, for this integral, what's changing is the y. Remember, that's supposed to be the dy there. What's changing is the y. The t minus 1 is a constant, so I can just like pull it out. And there's also a minus, so when I pull out that minus, I'll have a plus. And what's left is the integral from 0 to infinity, y to the t minus 2 e to the minus y dy. But that is precisely the definition of the gamma function at t minus 1. See, t minus 2 is t minus 1 minus 1. And so it fits the definition. So what we found is that gamma of t is t minus 1 times gamma of t minus 1. So, like, say we needed gamma of 5. Well, that would be 4 times gamma of 4. And then gamma of 4 is 3 times gamma of 3, and gamma of 3 is 2 times gamma of 2, and gamma of 2 is 1 times gamma of 1, and gamma of 1 is 1. So we get 4 times 3 times 2 times 1 times 1, which is 4 times 3 times 2 times 1, which is 4 factorial. So gamma of 5 is 4 factorial. In fact, if you start with any positive integer n, then you'll get that gamma of it works out to n minus 1 factorial. Now, you can't do that for like a non-integer. Like if you try gamma of 5 plus 1, then eventually you would never come down to a gamma of 1. At a certain point, you would come down to a gamma of 0.1, and that would be 0.1 times gamma of negative 0.9. And then that, and you would keep on going down to these negative numbers. You would never latch on to a place where you could stop, and so you wouldn't be able to come to something definite. So you can't just find gamma for any real number. It's very rare, the real numbers that you actually can find gamma for. But for positive integers, you know that it's the integer minus 1 factorial. So if like some bizarre sorcerer were to come up to you with his like magic wand and say, tell me what 2.7 factorial is, or I will incinerate you with this magic wand. You know, rather than say, this is stupid, there's no such thing as 2.7 factorial, you could say, well, it's gamma of 3.7. Along the analogy with, what gamma was for positive integers. So the gamma function is sort of like this generalization of factorials to positive real numbers. It's amazing. So going back to the waiting times, we had the PDF for our waiting random variable capital W, and it was this. Okay. So I'm going to do two things. I'm going to go ahead and call the W X. Okay. And the other thing I'm going to do is see if I can like incorporate the gamma function. Watch this. So here I am just renaming the W to be X. Next up is I'm going to go ahead and use thetas instead of lambdas. Now theta is 1 over lambda, so when I rewrite with the thetas, it's going to work out like that. And then the alpha minus 1 factorial, remember alpha was this integer, right? And so alpha minus 1 factorial is actually gamma alpha. Okay. And so like, we look at that as a function, and we imagine like, what if alpha were not an integer, but just any positive real number? And the textbook goes and shows that if you actually integrate this from 0 to infinity over the support, then you get 1. It's not a hard job. It's just a little bit of change of variables in your integration with substitution. So I'd suggest go back, look at it, read it. So actually, you could define the gamma distribution not just for whole numbers alpha, but for any positive real number alpha. And so like if alpha is, 3.7, then it's sort of like you're waiting for the 3.7th event to occur. It's really interesting. So I think I'll stop there, and we'll look at some more facts about gammas and get into some related distributions and maybe do some computational examples in another screencast. See you later.